So now we are going to discuss a new theory called the Vsepr theory. Vsepr theory is used to predict the shape of the molecule in three dimensions. You might say, doesn't the Lewis structure do that for us? No, because the Lewis structure gives you the bonding between the atoms in a given molecule. As for what is the shape of that molecule in three dimensions, the Lewis structure doesn't do that. If you notice, you can draw the Lewis structure on a blackboard or a whiteboard, and it's all flat. The real structure may not be flat, may occupy space in the three dimensions. So that's where the Vsepr theory comes along. Vsepr stands for valence shell electron pair repulsion theory. The name looks very complex, but it's a very simple theory. And what does this mean? It means that the valence shell electrons, remember the electrons in the outermost shell are called valence shell. Those are the ones which are shared or transferred. Well, those electrons are all paired up. If you notice that they are in pairs of two. When you draw the Lewis structure for any of the molecules shown in the previous videos, you will notice they are all paired up. Those electron pairs repel each other, including the double bonds and the triple bonds. And when they repel each other, they are going to try to maximize the distance between them. And that's what's going to give birth to the right shape in which the distance has been maximized between each of the pairs. So let's look at some structures of different molecules, and let's also look at their Lewis structures. Then we will see what their shapes would be based on the Vsepr theory. Yep. And when we use the Vsepr theory, we are basically looking at the covalently bonded compounds, where there is the covalent bond is directional, having a specific orientation in space between the bonded atoms. It will all make sense when we look at actual bonds. On the other hand, ionic bonds have electrostatic forces with no specific orientation in space. That's why when it comes to ionic compounds, we don't use the Vsepr theory to predict a shape for the molecule, but when two compounds, rather a compound has two atoms bonded with covalent bonds, that's when a shape arises because the bond is directional. Here is an example. BeH2, beryllium hydride, is the name of this molecule. Now, this is the Lewis structure of beryllium hydride. If you remember, beryllium is one of those atoms with an incomplete octet. It doesn't have 8. Instead, it has 4. Each bond has 2 electrons for a total of 4. Now, with those 4 electrons, 2 on one side, 2 on the other side, is how you would draw in the Lewis structure. Right? You would not place them at 90 degrees or closer, but you would place them on the opposite side. It comes naturally to make it symmetrical. But it turns out that the actual shape is also the same as the way we draw the Lewis structure. Hydrogen on one side and the other hydrogen on the other side. This is where it shows the actual shape. And what's the angle made between the side atom going through the central atom, going to the other side atom? What is the HBEH angle? It's also flat, hence it's 180 degrees. So when you have 4 electron, uh, when you have a structure like this, 2 electrons on each side, and that's when we say it's flat or linear. Now here is BF3, boron trifluoride, and this is how we draw it. Try to make it linear, try to make it symmetrical, sorry. And when we do that, we try to put the fluorines on each sides of the triangle. And the angle between going through the central atom to the side atoms is 120-degree angle. And that's the shape of the molecule. This particular shape is called trigonal planar shape or trigonal planar structure. The angles between them are 120 degrees. And that's how the bonds repel each other and maximize the distance between each of them. Now, the shape is going to be different from the Lewis structure. CH4, if you were to draw CH4 out on a piece of paper, you are not going to show the 3 dimensions. It's going to be flat. You will make 90 degrees angle between going from hydrogen, carbon to the next hydrogen. But in reality, the shape is known as a tetrahedron shape or tetrahedral. And the angle is actually 109.5 degrees. Right? It looks like a four-sided pyramid with the carbon in the center and the four hydrogens on all the other four sides, including the apex and the four other sides. If we make this structure using something called molecular models, we can pick any of the hydrogens to be the apex, and the other three hydrogens would look like the tripods for this structure. Now, you can show this shape either using the model seen here, or you can draw it out in this way, where these two hydrogens shown with these straight lines represent the hydrogens which are in the plane of your drawing instrument, your paper or your uh, whiteboard. But this dashed line represents the hydrogen going away from us in the background, while this wedge line represents the hydrogen coming out towards us. The angle is 109.5 degrees, as I said previously, and is greater than 90 degrees. Remember, 90 degrees is what it would look like if you were to just draw the Lewis structure. And look at the Lewis structure of methane, CH4, in one of the previous videos. And in that case, you will see how symmetrical you drew it, and it's CH4, and it's all flat, and it looks like there are 90 degrees, but in reality, it's 109.5 degrees. And the shape is called tetrahedral. What about ammonia? Ammonia's Lewis structure is shown here. Ammonia has this one lone pair of electrons on it, and that complicates the matter a bit. This is the Lewis structure, and forget about the triangle you see there here. Draw the Lewis structure or go to the previous videos and see what the Lewis structure of ammonia looks like. With ammonia, you have three hydrogens and one lone pair. It is like tetrahedral, except the last atom is missing. Instead, on the apex, we are putting this lone pair. And because it's just a lone pair with no atom, there is no bond there. When we show it using our model, as shown here, our model kit, it just looks like a tripod with three legs. This shape is known as trigonal pyramidal shape. It's like a pyramid that has three sides, side one, side two, and the side in the back, trigonal pyramidal. Now you would expect the angles to be 109.5 as well, because it's basically the same shape as the shape where you have the central atom in the center and there are four sides of the pyramid, just like here. But the lone pair of electrons are much closer to the nitrogen than having another atom bonded here. As a result, those electrons repel the other three bonds more so, forcing the other three bonds to come closer and squeeze at the angle that is normally expected from 109.5 to 107 degrees. You don't have to memorize this angle. The angles produced when the lone pair of electrons are there, and we will see some other examples like that as well. But you should be aware that otherwise, the normal accepted angle for this kind of structure, where there are four atoms attached to the central atom, is 109.5. Just because one of the atom is now a lone pair, that doesn't mean that it's a totally unrelated structure. It still falls within the tetrahedral form, but we call this trigonal pyramidal structure. What happens when another atom is removed and now you have another lone pair? That's exactly how water is. H2O is not flat. And that's where it's completely different from how we draw in the Lewis structure. H2O is not linear going from H to O, then H on the other side with 180-degree angle. Instead, it is shaped like this. We call this bent or angular. There are two lone pair on the oxygen and they squeeze the other angle between HOH even further than what we saw in ammonia. And instead of being 109, the angle is squeezed down to 104.5 degrees. Okay. Why is this molecule not linear? Because there are lone pairs. The previous example where we had that linear molecule here, there were no lone pairs. And that's why it was linear. So with all that said, let's figure out how we can just look at the Lewis structure of a compound and know what shape it will have. If there are two bonded atoms with no lone pairs, the angle will be 180 and it will be linear. One example was beryllium hydride we saw earlier. Other example is carbon dioxide. Draw the Lewis structure of carbon dioxide and look at the central atom. The central atom has two bonded atoms, two oxygens, and zero lone pairs on it. Hence, it's flat, it's linear. And you must be able to draw the Lewis structure correctly in order to predict this. Otherwise, everything will be wrong. Then, if you have three side atoms with no lone pairs, 120 degrees, it's trigonal planar. SO3 is an example. The example we saw earlier was BF3, boron trifluoride. Okay, boron has no lone pairs on it and three side atoms. Then you have uh, two side atoms, but one lone pair. We didn't see an example of this earlier here, but there is an example molecule called sulfur dioxide. Draw this molecule and you will see that there is one lone pair on the sulfur atom in the center. And there are two oxygens on the side. Okay. The angle will be less than 120 because the lone pair pushes the bond angle to squeeze on itself. Then we looked at tetrahedral with methane, then trigonal pyramidal with ammonia, and bent with water. How do you figure out what's going to be the molecular geometry? And you have to memorize these names. You also must memorize the angles where you have to memorize 180 degree for linear, 120 for trigonal planar. You don't have to memorize exactly how much it will be if it's less than 120 in case if there is a lone pair, but it will be less than 120. That's all you need to know. And if you have tetrahedral with four bonded atoms and no side atoms, I mean no lone pairs, then it's 109.5. And depending on how many lone pairs you have, it will be squeezed to a smaller angle, but you don't need to know exactly what. All you need to know is to draw the Lewis structure correctly and count the side atoms or the bonded atoms and count the lone pairs. Based on that, you can make the assignment for the molecular geometry shown here. Yep. So that's how you do this. Two bonded atoms is linear, three bonded atoms, trigonal planar, four bonded atoms, tetrahedral. And if there are lone pairs, in this is the case when there are no lone pairs. But if there are lone pairs, it would be either angular or trigonal pyramidal. So you should be able to do this. Here is another molecule, a complex molecule called dimethyl ether, where you have oxygen in the center and two larger groups here. Don't worry about the shape. I mean, don't worry about the exact bonding here between the carbons and hydrogens, but just concentrate on the oxygen in the center. If it's in the center, how many side groups it has? This time it's not just one side atom, but rather groups. Well, it's one and one, two, and two lone pairs. So according to that, what should it be? It should be four, um, I mean, two bonded atoms and two lone pairs. So if you go to that table, two bonded atom, two lone pairs makes it bent or angular. And so that's what it would be. X for the exact angle, we are told it's 104 degrees, but we know it should be anything below 109.5 degrees. Here are some more problems. PCl3, SO2, PH3, and SiH4. First, draw their Lewis structures and then look at the central atom, count the number of side atoms and the number of lone pairs on the central atom, and then assign it the molecular geometry according to the Vsepr theory.